Hello, welcome again. We are covering the subject thermodynamics for civil services means IFS and various gate exam. Next topic in the chapter of availability is reversible work by an open system exchanging heat with the surrounding only. So here, suppose this is your open system and we are considering elementary things. Suppose elementary mass dm1 is entering the system and dm2 is leaving the system. Specific energy of this elementary mass is h1 plus v1 square by 2 plus vz1, and for mass leaving the specific energy is h2 plus v2 square by 2 plus vz2, and the system is producing work dw and taking heat dq, and in this process the energy of the control volume is changing by small amount, that is d bracket u plus mv square by 2 plus mvz. Sigma is for the surface. Okay, so we are now our topic is to find out reversible work by an open system. So here dq is input to the system. Okay, and the suppose the system temperature is T. Okay, and the surrounding temperature is suppose T naught. If the heat is supplied from the surrounding to the system, that is at temperature T naught, and the system is at temperature T, so then this will not be reversible. So to make this dq reversible, we will assume an engine operating between atmosphere and this surface. From atmosphere, this engine is taking heat, that is dq naught, and producing work dwc, and rejecting heat to this control surface of control volume, that is dq. Okay, so such that dq naught by t naught will be equal to dq by t, which will make this engine reversible and this heat transfer also reversible. Okay, so now if we apply the first law to this control volume, okay, then the energy entering the system are this energy, heat energy, energy leaving the system are dm, this energy and this energy. So dq will be plus entering, this will be plus entering, this will be minus leaving, dw is also minus leaving, so this will cause change in energy of the system, that is this. Okay, so this is your first law applied to this control volume or open system. So this is equation given by equation 1. Okay, so now we'll modify this equation 1 also. So as this is this heat transfer is reversible, to make it reversible, engine has been assumed. So it means dq naught by t naught is equal to dq by t. Okay, and the engine is producing work, that is dwc, that is your difference of heat, so that will be dq t naught by t minus dq, or dwc will be at dq from this dq is dq bracket t naught by t minus 1. So this is equation number 2. So now this dwc will always be positive, because always positive is if here T naught is greater than this T, this surface temperature, then the dq naught will flow like this as shown, and dq will also flow from the engine to this control surface, and work will be positive. If suppose T is greater than T naught, then the direction of dq will change, get reversed, and dq naught will also get reversed, but then the work done will be a dq minus dq naught, and dwc will be always positive, because then dq will be more than this dq naught. Okay, because t is more than t naught. So dwc will be equal to dq t naught by t minus 1. This is equation number 2. Okay, and this will always be positive. Now we will consider entropy. So as we are considering the process be reversible, so there will be no entropy generation. So entropy change in the system will be the entropy change due to heat, that is dq by t, and entropy change due to mass, that is dm1 s1 minus dm2 s2. Okay, from this we can get dq by t as ds minus dm1 s1 plus dm2 s2. This is equation number 3. Okay, and now the work done by engine is dwc, and work done by open system is dw. So total work will be here dw max or dw reversible is dw plus dw. Now dwc from equation 3 can be put this, sorry, from equation 2 we can put this. So it will be, so dw max will be here dw plus dq bracket t naught by t minus 1. This is equation number 5. So now our equation number 1 is in the form of dw. So we can put the value of dw from this equation 5. Okay. So this will be your dw max. So we can put, or we can put the value of dw here. Okay, so dw max will be your dq plus energy entering minus energy leaving plus change in energy of control volume plus this term. If we further solve it, then we will get this energy entering, this part minus this part minus this part, and this part is being solved, that is dq by t into t. So now dq by t can we can put this value. So this will make equation number 7. Okay. If we put the value of dq by t, this, then this will make this, and if we modify this equation, then it will be, we'll take this dm1 s1 or here, or s1 here, or t naught s1 here, okay, and t naught s2 here, and this u t naught s t naught ds means t naught ds means t naught is constant quantity, so ds is differential, so d we have taken outside, so it can be written as t naught s. So this is equation number 7, and this is the general expression for the work done in an open system exchanging heat with surrounding. Now if we consider the find the reversible work in a steady flow system. So in this equation, in steady flow process, dm1 will be equal to dm2 equal to dm, and there will be no change in energy of the control volume. So this will be 0. Now this equation 7 will reduce to here, this will be 0, this dm2 and dm1 are equal, so the work done will reduce to this equation number 8. You can put it dm1 and dm2 as dm. This is equation number 8. So if we take if we integrate it, then we'll find out the w max. Okay, or it will be m h small h1 into capital H1, and this will be t naught s1. This will be mb1 square. This is mgz1. This will be h2. This will be t naught s2. This will be mb2 square. This is mgz2. Okay. So now w max can be written as this, taking this h minus t naught as Keenan function. This is your dy, that is Keenan function, and this whole can be taken as availability function, that is the psi 1, and this is psi 2. So this is your formula for w max. Okay. So if change in kinetic energy and potential energy is neglected, then w max will be h1 minus t naught s1 minus h2 minus t naught s2, or we can say difference of Keenan function.